All right, let's do another one all the way through. So feel free to pause this and try it yourself and check your answers if you're ready. We're given a rational function here, and we want to find critical values, we want to classify, we want to find inflection points, and we want to sketch. So for critical values, you take the derivative. We're going to have the bottom squared, and then the bottom times the derivative of the top. You could multiply the top out, but you can also do a chain rule here. We have stuff to a power. So the 2 drops down in front, the new power is 1, and then we would chain out the derivative of x minus 1, but that's actually just 1, so this one works out nicely. It's like you don't even see a chain rule. And then we would need x minus 1 squared times the derivative of x squared, which is 2x. In terms of simplifying, this is a great one for looking to factor out a common factor. Both terms have an x minus 1, both terms have a 2, and both terms have an x. So this is split right in the middle. The minus sign is what splits it into 2 terms. From each of those, I can take out a 2 in x and an x minus 1, and I will be left with a single x, because there was 2 of them in the first term, and a single x minus 1, because there was 2 of those in the second term. So in the brackets, I have x minus x plus 1. So that gets even better. That's just 1. X minus x drops out. So really, all I'm left with on the top, hold on, let me write my denominator first, x to the 4th. All I'm left with on the top is 2x times x minus 1, but writing that denominator made me realize I can take out a single x from that as well. So I get down to 2 times x minus 1 over x cubed. That's my k prime of x. And I want to know, when is it 0, when is it undefined? This is reminding me that it would be good to state my domain up at the beginning. So my domain is all real numbers except for 0. So x can't be 0, which means when I'm looking down here and I say it's undefined at x equals 0, that is important, but it's not a critical value, because in this case it's an asymptote. It can be other things as well. It's some kind of discontinuity. The function is also undefined. So if the function is undefined, you can't include it as a critical value. If I want to know when k prime equals 0, that ends up meaning that we just need the numerator to equal 0. The only way to make a fraction 0 is if the top is 0. And I would say first step, just divide by 2. Get rid of it. You don't want to divide out your variable, but it's no problem to divide out a constant like that. So my one and only critical value is at x equals 1. So I have a domain problem at 0, a critical value at 1. I'm now supposed to classify using first and second derivative. So again, just running through both ways. You do not have to do both ways every time, but make sure you're practicing both ways. For a first derivative, we're going to go ahead and start our sign chart. We're going to say at x equals 1, the derivative is 0. We're also going to remind ourselves that at 0, both the function and the derivative are undefined. So we don't care what's happening around 0, but we do care what's happening around 1. And this is a great example of why it's important that you include that discontinuity on your sign chart. I think a lot of people would put that 1 down and then they'd try and test 0 and they'd get undefined, and it can be really confusing if you're not thinking about what that means. So what I need to test is something between 0 and 1. I'm going to test x equals 1/2. And when I test, I'm testing the first derivative. This is first derivative test, so I'm testing the slope. So first derivative's here. When I plug into that simplified version of my first derivative, I get 2 times 1/2 minus 1, which is negative 1/2, divided by 1/2 cubed, which is 1/8. All I really care about is sign. So in the top, if I multiply, I'll get a negative number. And in the bottom, when I divide the negative by a positive, it stays negative. So it's negative between 0 and 1, which means the function is decreasing. So probably coming from an asymptote and decreasing and then hitting a flat spot. And then if I test over here at, say, 2, I get 2 times 2 minus 1, which is 1, over 2 cubed, which is 8. And those are all positive. So it is going to switch to increasing. It's rational, so there's probably a horizontal asymptote. And let's just look at that and think. We want to look back at the original function. At 1, interesting. So it's probably coming up and doing this. You don't have to get this at this point, but I'm thinking ahead a little for later. It'll probably come up and level off at 1. But for sure, even without that, I can say that there was a local min at, what was it now? X equals 1. That was my critical value. And since I know I'm going to graph later, I'm going to go ahead and plug that back into the original function to get a y value. When I plug 1 into that k of x, I'm looking right here, I get 0 on the top. So it's 0 over 1, which means the point is 1, 0. So there's my min. If I wanted to do this with second derivatives, I think this is maybe still a little bit of a messy one. But let's see, I would take that 1 in the box. That's pretty simplified. In fact, I'd even multiply it out so that I don't have to think about those parentheses. I'd think about 2x minus 2 over x cubed. The second derivative, we'd need the bottom squared. So x cubed squared is x to the 6th. And then we need the bottom. The derivative of the top is 2 minus the top times the derivative of the bottom, which is 3x squared. And I would say it's not a bad idea, again, we could factor out an x squared, but there's also a 2 in there. So maybe this time I'll distribute and then factor, just so you can see a couple of different options. 2x cubed, and then I need to distribute through the minus and the 3x squared. So negative 2 times 3 is 6x cubed, and then it becomes positive, and we're doing 2 times 3x squared, so 6x squared over x to the 6th. And I can combine a little. I get 6x squared minus 4x cubed. And now I'm going to do the factoring, and I can get the 2 and the x squared both at the same time. I'll be left with 3 minus x, a little scrunched. Okay, so that's my second derivative, and I can even do a little better than that. I can cancel out the x squared, so I'm left with 2 times 3 minus x over x to the 4th. So that's my k double prime. So that wasn't too bad finding a second derivative, a little bit of mess, but it didn't take me long. From there, remember, you don't need a sign chart. All you need to do is plug in your critical values. So this time I only had one critical value. It is a flat spot. That's really important. If it's a corner, if it's an undefined, you can't use this. Okay, so we're going to get 2 times 3 minus 1, so 2 times 2, over 1 to the 4th, we're getting 4, which is greater than 0, which means at our flat spot, our horizontal tangent, the graph bends up, which means it has to be a minimum, which is, again, what we concluded up above. So we're just showing the 2 different ways to do it. Okay, last thing, we want to find our inflection points, and then we want to sketch everything. So we've already got a k double prime. K double prime was 2 times 3 minus x over x to the 4th. And to find inflection points, we want to know when is that 0 and potentially when is it undefined. But again, it's undefined because the function has an asymptote, not because there's an inflection point. So at x equals 0, but that'll be good for our sign chart. The only time that the numerator equals 0 is if x equals 3. So we have one potential inflection point. I wish it had a name like critical value, but they didn't make up a name for this that I know of. So we'll just say we potentially have an inflection point at x equals 3. To verify, we'll do a quick sign chart. We'll say, okay, at x equals 3, the second derivative is 0. We will mark off 2, 1, 0 way over here. I don't know why I made that so big. That's okay. At 0, the function is undefined, so we want to make sure we plug in something between 0 and 3. If you plug in -1, it might give you not the best information. So I'm going to plug in 2, and I get 2 times, plugging into the second derivative, 3 minus 2, which is 1, over 2 to the 4th, which is 16. So I get positive 1/8. So it's concave up. The function is concave up. And then if I plug in 4, I get 2 times -1 over 4 to the 4th, whatever that is, something big. And that is definitely negative. So it did switch concavity. There is an inflection point at x equals 3, and if we plug back into our original function, I'm going to write it down here because I'm going to need it anyway. Y equals x minus 1 squared over x squared. So if we plug in 3, we get 2 squared, which is 4, over 3 squared, which is 9. Okay, so we have an inflection point at 3 4/9. We have a minimum at 1 0. Global behavior can be really helpful. Let's start to sketch here. 1 0. Okay, we had a vertical asymptote at x equals 0. We already decided. Inflection point at 3 4/9. So I'm going to make this 1. 4/9 is about 1/2. So this is an inflection point. This is a minimum. I can also say, oh, well, I guess I already kind of got that. Looking at this equation of the original function, there's an x-intercept at 1, but I've already got that. I can look at that and say since it's squared, it's going to be a bounce. So I'm probably doing this. And then global behavior is what I said I was going to look at. Here, if we multiplied this all out, the biggest power on the top would be an x squared, and it would have a 1 in front of it. And the biggest power on the bottom is also an x squared with a 1 in front of it. So the top and the bottom basically tie as we start to plug in really big positive or negative numbers. So an x squared over x squared is going to start getting really close to 1. We have a little bit that we're adding and subtracting in the top, but the bigger the numbers get, the less that matters. So I think I'm seeing this has to approach the asymptote, right? We have to go up towards the asymptote. I can't turn around and head down because I don't have another x-intercept. This comes up and it changes concavity. That's a little funny looking. So it's going to go from concave up to concave down. Hideous. I don't know if I can make it much prettier though. Right there. And then on the other side, since everything is squared, it's also going to be going up. So I think it'll just do this. So you can plug in some more numbers to help you out as well. And like I said, this is a little tricky, and you have to remember some things from 142, but do your best. You can check with technology. And we're just trying to do the best job we can without technology. Okay, thanks for watching.